Welcome you all. Hope you enjoy this. Let's get started. We'll just go in order. Thermo first. Thermo first. Okay, let's start with some of these terms before we get to a specific example. This will lead us into a calorimetry talk here. Okay, let's go through some definitions first. Is this heat or work? It's really a heat. A really simple definition is a heat at constant pressure, but comes from the first law. Delta U is Q plus W. So if you have a system, then across the boundaries, only two things can flow. That's Q, heat, or work, W. So delta H, or really delta H, is in the heat category. It's a heat at constant pressure, or if you rewrite the first law, like this. So I put the work term in, P delta V, and got the delta H. If I solve for the delta H, this is another way you could represent what delta H is in terms of other variables. The internal energy, U, would be like the total energy. Another way to say the total energy. It's the sum of all the energies when you account for, say, the kinetic energy and the potential energy and all those sort of things. So we might, in a simple way, say it's the total energy of, that we're dealing with. So that's why the change in the total energy between the system and the surroundings is whatever goes across the boundary. So heat or work. Okay? Q reaction, these are all the terms I was asked about. Q reaction is the heat of a reaction, or the energy of a reaction. Often we'll label this as delta H. Technically, that's delta U. So technically it's delta U, but because the work term, this term right here, tends to be small in most all scenarios as far as chemical reactions go, or negligible, then you can see that delta U and delta H are equal. So we'll be talking about delta H. Let me show you something in my reader. I think this was at the end of chapter 12. Once I find a page number, I will tell you. But there's multiple ways to be solving for delta H, some of which we'll cover tonight because you asked. This is the bottom page 35 and 36. Okay, so again, delta H and delta U are pretty much the same. As far as we're concerned, because the work term is negligible, there's multiple ways to find delta H. Let's go through those just to make sure we got that. Something I call conversion. I don't think anybody asked about that tonight. You may or may not have a reaction, but the weird thing is that we ask for delta H and you have a delta H in the question. But the delta H given is not per the amount that is asked about. So you just have to convert it to the amount requested. Hess law, we'll do one of those tonight. That's where you have multiple reactions. Enthalpy of formation, that's where you definitely have a reaction, but just one that you care about. I'll cover that. Somebody asked me about that. Calorimetry is another way to do it. A couple people asked about this. Usually it's a coffee cup calorimetry, but bomb calorimetry could work as well. So these are, again, all ways to find delta H. And then two less common ways you see here at the top of this page. 36. Cloch's clapeyron has a delta H. Which delta H is in Cloch's clapeyron? Vaporization. So they ask for that, and you have two states. You can use that law or that formula. And then, of course, the first law of thermodynamics. Delta H is delta U plus P delta T. The equation I just had written down. Those, as far as 2B is concerned, are the ways to find delta H. Okay? Let's go back to here. So there's multiple ways to cover find delta H. We'll cover some of those tonight. Cube reaction can also be found through calorimetry. So we're going to do a little bit. Let's do a little bit of calorimetry. Your instructor may set it up differently than me. So if you like that instructor style, keep with theirs. The way I set a calorimetry problem up is the sum of the Q's equals 0. That means the sum of the heats going across the system boundary will equal 0. What goes in will equal net what goes out. So it'll be a conservation of energy, really. Okay, so this can take place in two categories. The coffee cup calorimeter, that's what you're doing in lab, that style, and then the bomb calorimeter. Okay? All right, how do these styles work? Well, this will have a lot of delta H's, or Q's, delta T's, things like that. So let's go over to the bomb first. That's a little bit more similar. When you set up for a bomb calorimeter, it almost always sets up the same every time. There'll be a Q reaction plus, I have to fit this down here, a Q calorimeter. So the bomb calorimeter problem always includes the calorimeter. So you have to include that term. So it'll end up like this. 0 is Q reaction. That'll be basically a delta H term. Plus Q cal, C delta T. And then you're going to solve for Q reaction, and that'll equal negative C delta T. Usually this is one of your steps, typically the first step to do this. So you'll be given C, you'll be given delta T, you find the Q reaction. And then the next step, usually, but this can be done in reverse order, is you're going to take that Q of reaction and divide it by the amount given. It depends on what units you're given and what units you solve the Q for, but whatever the amount is, usually you're going to divide by that. So you get a kilojoules per gram or kilojoules per mole. Usually pretty easy steps for the most part. So that's the more straightforward one. The coffee cup calorimeter can be a bit more complicated. Now, in both cases you would do this, but the coffee cup calorimeter, because it has sources of Q that are sometimes harder to find, it's usually easier to think about. I always think, okay, what are all my sources of temperature change? Or what are all my sources of enthalpy change? So I need to list down all my things that change temperature and all the things that change enthalpy. Okay, enthalpy is sometimes a confusing one. Enthalpy is not a temperature change. Okay, it's not a temperature change. So that could be what three things? Phase, solution. So you're mixing a solution together. Sometimes your textbooks will call this a reaction, but I separate from the reaction. A reaction would be A plus B goes to C. A solution would be I'm putting a solid, say a salt, in a solution and it just dissolves and becomes aqueous. Okay? So something that's a solid and becomes aqueous. Or it could be two liquids that just mix together. That would be a solution as opposed to a reaction. But sometimes you'll see those put together. So you need to find all of those. Okay. If it is a delta T, then you're going to use MCP delta T. If it is a delta H, you'll use N delta H typically. Usually it's some amount that's going to multiply by the delta H. Depends on the units of delta H. For example, if delta H is in kilojoules per mole, then you need to get rid of those mole units by multiplying by moles, N. Or delta H could be saying kilojoules per gram, and then you need to multiply by a mass. Whatever it is, to get rid of the amount unit in the denominator, so you're just left with joules. Kilojoules are really joules, is probably going to be the most helpful. Okay, so let's see what an example setup might be of a coffee cup, since those are a little bit more complicated. And I had a couple of questions that were related to it. Okay, let's say this is the coffee cup. Let me do two different examples because I was asked about two different kinds of questions. Let's say in here, there you go. Reaction occurs in a solution, let's say in water. So this is water. Okay. A reaction occurs, let's say it's exothermic. Okay, so reaction occurs, it's exothermic. After that reaction occurs, the water warms up. Okay, so there's a new final temperature. So what you would do is you'd say, okay, let's make this up a little bit more. You'd say, okay, The sum of the Q's equals 0. What Q's are there that change temperature? Well, the water will warm up. The calorimeter will warm up. Or the container, whatever the container is. And that's it. And then there's one more Q. What's the last Q? The reaction. Okay? So we'll go 0 equals. Now some of you, your instructors or whoever, they might say Q reaction is negative the other ones or whatever. That's the next step after this. It really depends what you're solving for. Let's say we are solving for Q reaction or the delta H. Well, we'll get there in a second. Q reaction. I want to rewrite it so I have more space. Okay. How do I know whether or not I use Q cal? Okay. If you're given the heat capacity, then you'll use it. So if they literally say the heat capacity of the calorimeter is blank, or is solved for the heat capacity calorimeter, you'll use it. Otherwise, in most cases, this is going to be negligible or near 0. Okay? In most cases, especially for coffee cup, not for the bomb calorimeter. You have to have it there. All right? So then you'll say, okay, this is going to be some probably N delta H term because it's a reaction. This will be mCp delta T. Okay? So then say you wanted delta H, you would say N delta H is equal to negative mCp delta T because they were equal to 0. And delta H is mCp delta T divided by N. Again, it depends on the units of delta H. Here I'm assuming the units are in joules per mole. So thus I have an N term here. Okay, the moles, so let's confirm that we're clear on this. The moles will refer to the moles of the reaction. Okay? Or whatever that amount is where my pen is. This one will refer to the water. Okay? So, as long as the water is the only thing warming up. So whatever is warming up will have to be in this place of the Q, in the numerator. Sometimes, if it's water, I'll put this as a side note, they'll give you the density and the volume. So to find the mass, you have to use this kind of formula to plug in there. Fairly common. There are two variants of this. What are the two variants? When this is for a reaction, I could have easily said if you mix two things together, and then it caused the thing to warm up. It would be the same sort of thing, except this would be the enthalpy of solution. The moles here would be the moles of whatever was mixed together. Okay, the total moles of whatever was mixed together. Let me say a little bit also about the phase change. Let's say I put something in there, even if it was a reaction like this, and it caused the water to warm up so much it boiled. Okay, so I had a reaction. The reaction was so exothermic it warmed the water up to the boiling point. If that was the case, little dash line here. I'll write a little bit more below. Missing one pen. Of course, it's golden. Okay, here it is. Okay. If the water was warmed up to the point of boiling by the reaction, then you would have to do this. Add another term, it's also boiling. Let's say it boils, but not all the water necessarily boils, but some of the water boils. Again, this would be an N delta H. This would be the enthalpy of the reaction, and this would be the moles of the things that are reacting. This would still be mCp delta T. What would T final be? Yeah, if it's boiling, T final would be 100 degrees C. Okay, what formula would I use here? Again, N delta H. What's the subscript for this delta H? Not fusion, vaporization, okay. So it's vaporizing or it's boiling. So that'd be a given number on your exam. You'd have to be given the delta H of vaporization. Okay, what is this? That is the amount of what? The amount of water. All the water? Not necessarily. The water that boiled. Okay, so that's the amount of water that boiled. Alright, so it depends on the setup. I just went through a couple just so you can kind of get the idea. Definitely do some examples. If you're in my class, I have a ton of every quarter almost. There's an exam, has one of these on there. Okay, questions on this before I go on? I'll give you a moment to think while I look for a Hess law problem. Somebody asked me one of those. I think I have it. All right. Questions? No? All right. My class, did I do this Hess law yet? Are you sure? Wow, okay, I didn't remember that. Blanked out that period. Okay, let's do another one then. I gotta zoom in for this one. Oh, wow. Okay, here we go. Oh, no answer. Get this. Yeah. Oops, almost saw the answer again. Okay. There we go. Okay, let's try that one. I don't think we did this one. She asked me for 10 to a last quarter. I think we did this for the final exam or something like that. Except for the delta H. We have one delta H. Okay. All right. So the Hess law, this is one where you'll have multiple reactions given. The ones overall, that's the one that's on the top by itself. Usually you're asked for that delta H, but you could be asked for delta H 1, 2, or 3. And then I'll typically give about 3 reactions on my average exam, but 2 is possible. 2 would be the minimum, and then of course it could be more than 3. All right, I have a particular, again, style of solving this. So I'm going to use my style. If you learn something else in another class, that's cool too. I just don't do it that way. All right, so let's do the way I do it. What I do, my step 1 is to take a look at the overall reaction and go through one molecule at a time, finding the compound that appears only one other time. So let's start here. Yes or no for this one? That's okay. People are saying yes. Let's check it out. It appears here and here, only twice. That's a good candidate. So I'm going to pick the color. Hopefully I have a lot of colors today. I'm going to do a purple circle around there and around here, or oval, or ovoid. Okay. So the overall reaction, that's the one on the top in this case, can't be changed. I can only change the second reaction, reactions 1, 2, or 3. I'm focused on the second right now. I'm going to multiply the second reaction by what? Minus 1/2. That means I multiply the delta H by minus 1/2. Minus means I flip it. That gets the Fe3O4 on the correct side, the reactants. Ooh, that's almost off screen. And the 1/2 gets it to be 1. Let's see if I can get it all on screen. Okay, that's better. All right, next. CO, is that a good one? No, too many times. FeO. Yes, I think that one works. It appears here. I'll do green rectangle around it. I think it only appears twice. Yeah. All right, I'm going to multiply the third reaction to match it by what? -3. The minus flips it to the other side, which is what I want. And the 3 puts 3 in front, which is what I want. So this has to be multiplied by -3. Whatever you do to the reaction, you do to the delta H. By the way, make sure you get this stuff down, because we're going to do the same kind of problem with different variables in about a chapter. So it's coming back. Okay. Only with something else that's called the equilibrium constant instead of everything. But it'll be way fun as well. Okay. Now, CO2, is that a good choice? No, here's too much. So I've exhausted step 1 of my strategy. Step 2 is to look at the intermediates. The intermediates are things that don't appear in the overall. What's an example intermediate? Yeah, Fe is a good one. Are there any others? Yeah, Fe2O3. Again, things that appear down here but not in the overall. I think, is that it? Okay, so let's just go through. Is Fe a good candidate? If it only appears twice, it is. Let's go brown. Yeah, I'm a brown poofy cloud. Okay, or sheep with no legs. Either way. Okay. These you have to cancel. They have to disappear. You cannot change the third reaction because it has a multiplier. You can only change reactions that do not have a multiplier. That's the first one. I will multiply by what? This is a -3 on the right, so I need a -3 on the left. So to get rid of that 2, -3/2 will do it. Okay? And let's zoom out so you can see how it's going to be all put together in the final answer. Right there at the bottom. Okay? I'll give you a moment to think about that. Let me know if you have any questions while I figure out what you want me to do next. Trust your math, you're done. All right, move this out of the way then. Let's take a look at what we've covered so far. Delta H formation is the last thing of Thermo. People who asked about the other ones, did I miss anything that you're interested in? Okay. Again, you can always ask me at 9. I just want to make sure, you know, we go a little fast, but I want to make sure I get through as much as possible. Enthalpy of formation. Oh yeah. I think I actually might have an example that I haven't done in class yet. Let's see. Maybe if I'm like this. Yeah. All right, let's try this one. This here, an enthalpy of formation problem, you'd only be given one reaction. You'd want the overall enthalpy, so it'd say what's delta H overall, something like that. By the way, what's the superscript 0 here? Yeah, you could say delta H naught. It means standard. That's usually a tabulated value at standard conditions. So it's usually a value you can look up in the table. Okay. So I'm going to do in black the things we're going to look up. Methanol we'll look up. So in black here, you're seeing everything we'll look up. This is in kilojoules per mole. We can look up the CO2. And we can look up the H2O. That was minus 286. There's one problem with the reaction. What's that? What's the problem with the reaction? It's not exactly balanced. What? I missed a what? What number? 2, thank you. Make sure to balance. I half balanced it and then I would realize I didn't finish. On a test, I would be very happy to not balance the reaction and you have to balance it. Okay? And that's a pretty common, we want you to be able to balance it. Now on the test, these black values written in black would be given. Except for this one, why is that? Oh, nice. It's in an elemental form. It'd be 0, so anything in elemental form. So all you'd have to do is go delta H is the delta H of formation values of the products. So one common problem, people don't remember to balance. Another common problem, so minus the reactants now, people don't remember the distributive property from algebra. And they don't carry the subtraction through. Luckily this one's 0, but they don't carry the subtraction through. So usually it's a sign error is what people miss. But that would be it. This is, I got mine, you can check my answer later if you want, 1454 kilojoules. 1454 kilojoules is what I got. There's a variant on this kind of question that's related to the definition. I'll do that in whatever this color is, blue. Okay, it might say something like, write the delta H of formation reaction for a particular molecule. Let's do that for the big one here, CH3OH. If you're writing the delta H of formation reaction, it's really related to the definition. Whatever they give you, you're going to put on the right-hand side of the arrow and only do one of them. So it'll be per 1 mole. And then you're going to write its elemental form on the left. So this comes from a carbon. That would be a solid or graphite. Plus hydrogen. Hydrogen in elemental form is H2 gas. And then oxygen. Elemental form O2 gas. And then you balance. Half oxygen, 2 of those, and 1 of those. So that would be the reaction that goes along with this in elemental form. So that could be a variant if you asked about the definition of where delta H formation comes from. Usually this is more of a multiple choice question. This could be, yeah, this is kind of multiple choice too. Sometimes it's part of a long answer.